Hello friends, welcome back to my channel, Physicist Buddhist in California. So in this lecture I'm going to talk about a conference that I just attended. So I'm a member of American Physics Society, and American Physics Society has a section, it's called Division of Particles and Fields. So this division has its regular meetings, and every 2 years they have a meeting called Pheno. It stands for Phenomenology. So people from all areas of particle physics, they are invited to present their latest research. By the way, so phenomenology, let me explain what that means. So in physics, one could say that there are three distinct divisions. One is theory, where people come up with theories to describe different phenomena of nature. And then there is experimental physics, which most people know. You basically do an experiment to test a theory, or sometimes, if you're very lucky, you discover something new, a new phenomenon which was not known. So then the theorists have to explain that. In between the two is another field called phenomenology. So phenomenology is that you take the data from the experiment or observation. Like for example, in astrophysics you can't conduct any experiment, so you just have observation. Like for example, you're observing the light from a distant galaxy, or even from our own galaxy, or even from our own sun, or you're observing the radiation from a neutron star or a black hole or a supernova. So then what a phenomenologist does, he or she would take that data and they would take a theory and try to fit the data to the theory. So it's called modeling. So you basically come up with a model that, using an existing theory, tries to describe the observation or the experimental data that you have collected. So this conference is basically focused on that. So they were phenomenologists, they were theorists, they were experimentalists, mostly because as the name suggests, the lion's share of the seminars and the talks were by phenomenologists, the well-known people in the field. They presented their data. I would talk about a couple of subjects that attracted me. So people talked about gravitational waves. About 10 years ago, gravitational waves were discovered, and this has opened a new window on the universe. So thanks to gravitational waves, we can look at the universe, what the phenomena that are happening in the universe, in an entirely different way. Before that, we were limited to electromagnetic spectrum, like radio waves, light wave, microwave, even gamma waves or X-rays. But now, thanks to gravitational waves, we can observe some phenomenon which could not be observed before. Like for example, the merger of two black holes, or a supernova when a star explodes in a supernova, or a merger of two neutron stars, or a merger of a neutron star and a black hole. So what exactly is a gravitational wave? So what happens when a cataclysmic event like merger of two black holes happens? Like these black holes, they are enormous. Each black hole has a mass of about 20, maybe 50 times the mass of our sun. So when they merge, because and this comes from Einstein's general theory of relativity, because there is so much mass coming together, and like Einstein's theory of relativity tells us that presence of mass curves the space around it. That's what that gravity is. So gravity is nothing but the curvature of space-time because of the presence of a mass. Now these masses are very, very large, so their presence and their motion through space-time leads to these disturbances in the space-time. So think of this as throwing a rock on a flat surface of water in a pond, and it creates these waves. You can see these circular waves traveling away from where you dropped the rock. So it's a similar process. So instead of the rock, imagine in your mind as these two black holes, and the surface of the pond is the empty space-time. So these waves basically they travel through the space-time and at the speed of light, and so they can be detected very, very far away. So for example, the first gravitational wave event that was detected back in 2015 happened 1.6 billion light years away. So 1.6 billion light years away, this merger of black holes happened, and this was detected in September 2015. So I was interested in those talks. They talked about the gravitational waves, and then there were talks in which they talked about neutrinos. And so neutrinos are subatomic particles, so they are pretty interesting. Their behavior is still not completely understood. We still don't know how much a mass of a neutrino is, and how a neutrino, one type of neutrino changes into another, like an electron neutrino can transmute into muon neutrino. There are three types of neutrinos, and about their antiparticles. Every subatomic particle has an antiparticle. So about neutrinos, it's not really clear whether they have distinct antiparticles or a neutrino is its own antiparticle. So that it's an open scientific frontier. And then there were talks about the quarks. So you know, inside an atom there is a nucleus. Inside the nucleus there are protons and neutrons. Inside a proton, each proton and neutron, there are three quarks. So how these quarks behave, how they interact with each other, what happens when these quarks come close to each other, and what happens when they move away from each other. So this is very interesting. The behavior of quarks is very different from the behavior of two charged particles, like for example two electrons. So when two electrons come together, they interact strongly, and when they go away from each other, from the Coulomb's law is inversely proportional to the square of the distance. So they interact very weakly. But in case of quarks, it's exactly the other way around. So when the two quarks are very close to each other, they are almost not interacting with each other. They are almost independent. And as they move away from each other, they start interacting strongly. And so it's like, imagine you have a spring, and you're holding two ends of the spring in your hand. So when the spring is not stretched, you don't see any force. But as you start to pull on the string, you feel you have to apply a force. So this is how the quarks interact with each other. So it's a fascinating subject. So yeah, so this conference lasted 3 days, and it ended this morning. And so that's about it. And I hope you enjoyed this lecture. And if you have any questions, please put your comments in the comment box, and I'll see you next time. Thank you for your attention.